Okay, we're going to talk about something called molecular orbital theory, which is part of module 1.2.3.2. I know it sounds complicated, but it's really not that bad. Okay, so what we're going to try to do is make this as simple and as painless as possible. Okay, and so first you say, oh, what the heck is molecular orbital theory and what does it represent? Okay, well, molecular orbital theory has to do with another way to describe how bonds might form. Okay, and so the idea is if the electrons in an atom are really described by atomic orbitals, then the electrons in molecules should be described by molecular orbitals, or MOs for short. And the other acronym that you can use to impress your friends is something called LCAO, LCAO, okay, which is linear combination of atomic orbitals, which basically says that we can construct or create these molecular orbitals by taking atomic orbitals and just adding them in different ways. And so we can add these atomic orbitals constructively or destructively, just like we added them to make hybrid orbitals. Okay? But because MO theory is a little bit more complicated, we're going to use this pretty much just for diatomic molecules. Okay, so when we create these molecular orbitals, there's a couple of rules that we have to follow. Okay, one is that total number of orbitals has to stay the same. Second one is that the total energy has to stay the same. If these rules sound familiar to you, they should. They're exactly the same rules that we used when we were making hybrid orbitals. Okay, the only difference is instead of calling them constructive and destructive, we're going to call them bonding or anti-bonding. Okay, and so the bonding orbital is one where it's basically constructive interference. The molecular orbital is lower in energy than the atomic orbital. The other possibility is anti-bonding, where the molecular orbital is higher in energy than the atomic orbital. There is this other thing called non-bonding, where the molecular orbital has exactly the same energy as the atomic orbital, but we're going to ignore that for now. Okay, and so what we're going to do now is I'm going to show you some simple pictures of MO theory so you can see how this works in practice. Molecular orbitals can arise from s orbitals or p orbitals. Okay, and so if you start with s orbitals, they can create sigma bonds. And what happens with the s orbitals is they add end to end, meaning I have one like this and one like this. These are the nuclei. One goes this way, one goes this way, and they overlap in the center. Okay, and so here's an example of a sigma bond or sigma bonding molecular orbital where they added constructively. Here's an example where they added destructively, which is anti-bonding. Okay, now instead of finding a lot of electron overlap in the center, there's actually a node in the middle, which means that there's zero chance of finding the electron in there. However, I don't have to create sigma bonds just from s orbitals. I can also create sigma bonds from p orbitals that are being added end to end. Okay, so here's an example of that. Here's one p orbital, and here's another p orbital, and they can overlap to make a bonding orbital, or they can add destructively to make an anti-bonding orbital. The interesting thing about the p orbitals, though, is they don't have to be added like this, end to end. They can also be added like this, parallel to each other. Okay, so if I do that, I create something called a pi bond. So here's how that works. Here's one p orbital, and here's one p orbital. And now these two pieces come together, kind of like goalposts in a football field. And they create one big lobe of electron density on top, and another one on the bottom. Okay, and so this would be called the bonding molecular orbital, where they overlapped constructively. And here's the anti-bonding one, where they were added destructively.